right, going on to chapter 16. So, whenever I teach this class, when I get to this point in time, I kind of feel like I've gotten over the hump of the semester. So, you as a student, hopefully, you're feeling a little better about yourself. You gotten over the hump of uh, dealing with acids and bases. Of course, the chapter on kinetics is the hardest chapter. We're still doing equilibrium, but it just feels easier. But so let's talk about this. We start this chapter talking about ethylene glycol poisoning. So that's if you drink antifreeze, for instance, or if a pet drinks antifreeze, the glycolic acid, your body will oxidize it to glycolic acid, and that'll cause the blood pH to drop. A condition known as acidosis. And part of the problem with acidosis, and there's several things. It decreases your oxygen carrying capacity of your body. It also, if it gets severe enough, uh, it'll denature your proteins, cause the patient to crash, cause organ systems to fail. But of course, the easiest one of the ways your body tries to get over this is by hyperventilation. So you hyperventilate, and then you get rid of the carbon dioxide, and it raises your blood pH. But truth be told, it's pretty hard to get to acidosis because your body has something called a buffer. A buffer is something that regulates the body's pH. Um, well, at any pH, and the buffer our body uses is carbonic acid and bicarbonate, so baking soda and fizzy water, basically. And it keeps our body's pH of around 7.3, 7.4 in that range is our body's pH. The cure for ethylene glycol poisoning, if you must know, actually is to get rip roaring drunk on ethanol. So, of course, don't go drink antifreeze and then get drunk. It's better not to go through the experience. But if someone um, does get ethylene glycol poisoning, the one of the cures is extreme intoxication with ethanol, but not to the point the person loses consciousness. The idea is that the person can prevent the alcohol, prevent the ethylene glycol from being oxidized, and then you can pee it out. So okay, but going back to this, our body obviously needs a way to regulate pH, and we do that with a buffer. And this is what a buffer is. It's a weak acid conjugate base or a weak base conjugate acid for buffers above pH 7. Most buffers are acidic, though, at least the ones that we use. So, for instance, acetic acid and sodium acetate, like I said, our body uses carbonic acid and bicarbonate. So, what does a buffer do? It resists the pH change. Buffer contains both weak acid and its conjugate base. Then the weak acid. So if you have a certain amount of like a pH that you want, and then acid is added to it, the conjugate base will neutralize the acid. If base is added to it, the weak acid neutralizes the base, and then it keeps the pH relatively constant. There's an equation here. So this is known as the Henderson-Hasselbalch equation. This is the x equals small approximation is included in here. pH equals pKa plus log of the base over the acid. And you can also, instead of using concentration, you can just use moles of base over moles of acid. So that helps for some of the calculations. And these are pretty easy to do. Let me give you an example problem here. What's the pH of a buffer solution? That's 0.05 molar benzoic acid and 0.150 molar sodium benzoate for benzoic acid. Ka is 6.5 times 10 to the minus 5. So there's the Henderson-Hasselbalch equation. So the pH is going to be the pKa is the minus log of the Ka, 6.5 times 10 to the minus 5, plus the log of the concentration of the base. The base here is the sodium benzoate. So because the sodium, right, it's the last chapter we talked about the acidic and basic natures of salts. So that one, always the base is going to have the alkali metal in it, or alkaline earth, usually alkali metal. And then the acid, in fact, it says acid, right? Benzoic acid, 0.05. So you just throw that in your calculator, and in doing so, you get pH is 4.74. Now, isn't that so easy? That is much easier, isn't it, than doing all the equilibrium stuff? Well, this is the equilibrium stuff, but it's already been done for you, so you don't have to figure everything out. So that's the Henderson-Hasselbalch equation. And this is something important. You will need this equation for other classes, especially ones that are heavy in biochemistry. So biology especially will use this equation quite a bit for pH calculations. Okay, and let's see if you can do this one. Uh, Try that one out. So I didn't solve this one. I can do it real fast. So see if you can beat me. My calculator's still loading. So it's 9.31 plus the, where's my log button? Log of the base. 0.17 divided by 0.25. And 9.14. It's C, 9.14. So it's that one. Okay, so next thing I want to do is talk a little bit about some of these graphs. So this graph is called a logistics curve. It's called a logistics curve because it's a log plot. pH is a log. And on the y-axis, there's the pH. X-axis is the volume of sodium hydroxide added. And this is it's a strong acid with a strong acid with a strong base. So a couple things to note here. You start off in a very acidic pH and you end up in a very alkaline pH. So it goes from acid to base. And notice that there is a point here. That is the equivalency point. This is where the moles acid equals moles base. It is also where the second derivative of the graph equals 0. And the second derivative means a concavity. Meaning if you look at this, so let's switch to orange. If you look up here, this graph kind of goes up. That's called concave up. And then this part goes down, concave down. And where it switches from concave up to concave down is right there at the equivalency point. So right there at pH 7. And that is known as the second derivative hitting 0. And I'm saying these things because if you look at these graphs, you can tell you certain things. And you can also look to see, you yourself can look to see where the second derivative hits 0. You can tell you information about graphs, and these graphs have information in them. So of course now we rely quite a bit on computers. So here's a strong base and a strong acid, so it's really just the opposite. You start off at a really high pH and you go to a really low pH, you have a concavity going up and you have the same equivalency point, and the equivalency point's at 7. And that's where the second derivative hits 0. And let's go on to a weak acid and strong base. And notice a couple things here. First of all, there's a sharp increase. So right there, where you have, on the other hand, if you look at the strong acid, strong base, it's kind of a smooth going down you have initially. And you have the sharp is really close to the equivalency point. Here, you've got a pretty sharp jump. And that's for a weak acid and a strong base. And notice, though, you have another concavity curve. You have concave down, you have concave up, you have concave down here. So you have two parts on the curve where the second derivative hits 0. And this part here, that first inflection point is also the pKa of the acid. So that's one way you can figure out the pKa of an acid is you can graph it and find where the second derivative hits 0. And also, notice here, this area here, I'll highlight it. That's the buffer zone. That's where so buffers only work over a range. And the buffer, so a different buffer works for different points. And then another thing to note, the equivalency point, this is above pH 7. So for a weak acid and a strong base, the salt is going to be pH above 7. So remember that when we talked about that the previous chapter. talking about the different strengths of the salts and that kind of stuff. If it's going to be, you have a weak acid, strong base, it makes it a alkaline salt. So it's there above pH 7. And also here, likewise, is a weak base and a strong acid. So a couple things, you have the initial really big drop, then you have a concave up, concave down, concave up, and you have the equivalency point. This, of course, is also the pKb, and then the equivalency point here, this is below pH 7. So the with a weak base and a strong acid, it's going to have an acidic salt. And then over here, for polyprotic, you can see there's still the initial jump because it's a weak acid, and you're going to have an inflection point here. You can see where you have these inflection points. So this is going to be the pKa1, this is going to be the pKa2, and notice also where the different equivalency points are. Since this is may not necessarily be pH, is pH lower than 7, depends on the weak acid, because it's polyprotic, it's got more than one. So you can still have the pH there be below 7 for the second hydrogen. But notice you have the concave down, concave up sections, and so on, where you have the second derivatives hit 0. So really you have a couple parts where the second derivatives hit 0. And also you have 2 buffer ranges. So you have 2 places that you can have a buffer in this diprotic acid. And this one's nice. It has a pH slightly above 7 that you can use for a buffer. So if you need that one. So there's different ranges, and depending on your range, you are going to use different buffers for different applications. So hopefully that's helped you look at some of the graphs and what they mean. And but join us next class for we talk about other aqueous equilibria. We apply equilibrium to other stuff.